Hello everyone, welcome back to our RAG series, one of the most widely used technique in modern generative AI application. So in the previous chapter we explored what RAG is, why it is needed and the limitations of traditional LLM models and how hallucination occurs and how the RAG pipeline works behind the scenes, and we also understood the traditional LLM workflow along with RAG workflow and learned the core fundamentals of using RAG with generative AI. So in this chapter we are moving to the advanced concept of RAG. In that we will try to understand what chunks are, why chunking is needed, how chunks actually work internally, what embedding models are, how vector search works, what hybrid search is, and other advanced RAG concepts including prompt engineering for RAG. So this chapter will be a little bit theoretical but extremely important because understanding this concept will help you to know exactly what happens behind the scenes when LLM powers the Gen AI application using RAG. So sit back, relax, and let's get started for chapter 2 of our RAG series. So let's begin. So now let's try to understand what a chunk is in the context of RAG. A chunk is simply a small, meaningful piece of larger document. So instead of sending a long PDF, huge block of text into the system, we break the content into a smaller and easy to understand section, and each section is called as chunk. So in simple, chunk is equal to a small meaningful piece of large document. So let's try to understand this with some example. So let's assume we have a 10-page PDF and we want to load the PDF into vector database. So we cannot store the entire 10-page document as one single unit. So what we do, we break the PDF into a smaller parts such as heading, paragraph, section, subsection, and some summaries. So each of these smaller piece is considered as chunk. We divided the PDF into a small chunks, that chunk 1, chunk 2, chunk 3, and chunk 4. So the original document may be 10 to 20 pages long, but before indexing, we convert it into clean smaller blocks called chunk. So now let's try to understand why do we need chunks. So LLM have a context window limit, which means they cannot process very large document in one go. Too much text leads to slower the retrieval process. So too much irrelevant text increase the hallucinations. So by dividing the document into a smaller chunk, which will helps for retrieval become faster, results become more accurate, and the system become less memory consuming, and hallucinations are reduced significantly. So chunking helps the model to focus on only the relevant part of that document. So imagine we have a PDF which contains introduction, refund policy, cancellation rules, and terms and conditions. So during the chunking, we divide or we convert those parts into a small chunk. Like in chunk number 1, we add introduction into it. Then refund policy, we'll put it in chunk number 2. Then cancellation rules, we put it in chunk 3, and terms and conditions we kept in chunk number 4. Now suppose the user asks question like, what is the refund policy? So instead of giving the entire PDF to the model, the system retrieves only the refund policy chunk from the vector database and sends to the LLM model. And then LLM then generates a cleaner and accurate answer based on that chunk. That's exactly why chunking is so important. So now that we clearly understand what a chunk is and why chunking is important, so now it's time to explore the different type of chunking strategies used in RAG system. So chunking is not a one size fits all process. So depending on your document type, accuracy needs, and retrieval requirement, different chunking strategies are used. So let's break them down one by one. The first type of chunk is nothing but fixed size chunking, breaking the document into a equal sized pieces regardless of sentence or paragraph boundaries. Which means imagine a long paragraph of 12,000 characters. If your chunk size is 400 character, then the system will simply cut content every 400 character and divide it into a chunk 1. The first 400 character will keep put into the chunk 1, then remaining 400 to the chunk 2, and the last 400 will go into chunk 3. Even if the sentence gets split in the middle, it doesn't matter because the size is fixed. Then number 2 type is natural language chunking. This method respects how human naturally write. For example, chunks are created based on the natural language boundaries such as paragraph, heading, bullet points, and section. For example, we writing the content or later in this format. So we put the bullet, then we write the paragraph, adding the bullet points and section. This is divided into different chunks. For example, the entire paragraph 1 is going to the chunk 1 and chunk 2. This maintains the original flow of the document, which makes the retrieval more relevant and more accurate. Then number 3, that is recursive chunking. So recursive chunking splits the document into different manner. So it splits by heading, splits by subheading, split by paragraph, then smaller parts if needed. For example, a PDF with chapter, section, subsection, and paragraph, each level gets progressively chunked. This is nothing but the recursive chunking. And number 4, that is overlapping chunking. So the overlapping chunking, each chunk is overlapped with the next chunk by 10 to 20% to preserve context. For example, if one sentence is cut between two chunks, the overlapping ensures both chunks contain enough context to understand the full meaning. So now that we clearly understand what chunks are, why chunking is needed, now it's time to learn one more most important concept in RAG, that is embeddings. So this part is real magic behind retrieval augmented generation, because embedding helps the system to understand the meaning of your text, not just in the word. So embedding is nothing but a numerical representation, we call it a vector of text that capture its meaning. So instead of storing your text exactly as word, the embedding model converts it into a list of numbers, usually hundred or thousands of number, which represents its meaning, context and relationship inside the text. So the word converted into numbers, sentence converted into numbers, and chunk converted into number. These numbers are called vector, and then they are stored inside the vector database. So let's say we have a PDF with the line that is what is the refund policy. Then the embedding model converts the entire chunk into a long list of number like you can see on the screen. Now imagine a users ask a question, then the question is also converted into the vector. Because both vector are mathematically close to each other, then the vector knows these two text or the text meaning and it retrieves the accurate chunk. So in this way, this embedding helps to retrieval the accurate data. So when we send a piece of text to an embedding model, the model reads the text, it understands the word, grammar, context, and meaning, and it finds the relationship like similar word, intent, topic, and then it places this text into a point inside a high dimensional vector space. And you can imagine this space is like a giant 3D map. So instead of three-dimensional embedding can have hundreds, thousands of dimensions. And the embeddings work for all the content types like text, PDF, website content, audio transcripts, chat messages, and even image. So now the next advanced RAG concept is vector search, one of the most important part of entire RAG system. So vector search is equal to finding the most meaningful and similar chunk by comparing embedding vectors, not with keywords. In traditional search, chunks are exact words, but in vector search, chunks for meaning. So that's why the vector search is also called as semantic search. So let's say a user asks questions like how I can get money back, but document chunk says our refund policy allows returns with 7 days. So if we use the keyword search, there is no money back, then no get money back. So keyword search fails with no match. According to that, vector search measures the semantic similarity between their embeddings and realize both sentences talk about refund. The meaning is similar, so the correct chunk must be this one. And accordingly, then it returns the chunk to the LLM model. This is what makes RAG accurate, context aware, and much smarter than the traditional search system. And then why vector search matters? Because vector search helps the system to find the right chunk even if the user uses different words, understands the meaning, not just exact matching, reduce hallucination, improves accuracy and enterprise RAG app, and handle natural conversational query. This is why almost every modern RAG system relies on vector database like ChromeDB and many more. So vector search takes embedding vectors, compares their similarity, and retrieves the most meaningful chunk instead of matching the exact keyword, giving more accurate, natural, and human-like results. So now let's talk about the next advanced RAG concept, that is hybrid search. So hybrid search is equal to keyword search plus vector search combined to give the most accurate and balanced results. So it uses the strength of both methods and merge them into a powerful retrieval technique. So using this hybrid search, the keyword search fails when there are some different words are used, spelling variations and other content or context is different than in sometimes vector search fails when exact keyword must match. Searching for code IDs or formulas, numeric or structured data is required. Since both have limitations, but the hybrid search solve the problem by using both together. So simply user searches, for example, refund policy for damaged product. Now look at two chunks. Chunk number one, refund available for damaged item with 7 days. In that, the keyword search score high because it contains refund and damaged. In vector search, it results medium because semantically matches but not perfect. And then assume chunk number two, the products received faulty are eligible for replacement or refund. Keyword search scope is very low or the vector search is high. So that's why the hybrid search combines both score and pick up the best overall match. So instead of depending on only keyword or vector search, hybrid search gives the most reliable, most relevant, and most accurate chunk. This is why the hybrid search is widely used in enterprise RAG system where accuracy is critical. So now let's move to the next advanced RAG concept, that is re-ranking. So basically the re-ranking is the process of taking the initial retrieval documents from vector search or hybrid search and then reordering them using the more advanced model, usually an LLM or a dedicated semantic ranker. So think of it's an final quality check to ensure the most relevant document appears at the top before the answer is generated. So why do we need this re-ranking? Because vector search is powerful, but it's not always perfect. Sometimes two chunks may have a similar embeddings, but one chunk is actually much more relevant and other is partially related to that topic. So a semantic re-ranker reads the actual text of each chunk along with the query and scores it based on context overlap, relevance, semantic meaning, and how well it answers the questions. This ensures the best document rise at the top, improving accuracy and reduce hallucination. So we'll try to understand this with simple example. For example, a user asks a questions like how to reset a password in Azure virtual machine. So the hybrid search or vector search may returns a document specific to the steps to reset Azure virtual machine password, which is a good match. Or second document that appears, that is changing the user password in Windows Server, which is a weak match. Or third scenario is that overview of Azure Resource Manager, which is a poor match. Then vector search found the document that related but not perfectly ranked. So the re-ranker does, it reads the query, the full text of each retrieved document, then it scores them, and finally it returns a perfect answer with the accurate document, which is helped to reset the virtual machine password in Azure. So now let's move to the final advanced RAG concept, that is nothing but prompt engineering for RAG. So what is prompt engineering for RAG? Prompt engineering for RAG is all about designing the right instruction format so that the LLM correctly uses the retrieved context chunk and generate an accurate, grounded, and safe answer. In RAG system, the quality of the final output depends heavily on how the context is passed, how the instructions are framed, how the model is restricted, and how the query and retrieved documents are stitched together. A well-designed prompt ensures that the LLM follows the context strictly and avoids hallucination. And how does it work? So without proper instruction, the LLM may ignore the retrieved context, then hallucination increase, then the model mixes the external knowledge with private data and response become inconsistent and unreliable. So the prompt engineering makes the model stays grounded in the retrieved chunk only. And how prompt engineering works? A good RAG prompt typically contains several structures, that is system instructions, user query, injected context, final output instructions, and saved and grounding rules. So these are the advanced concepts of RAG that are widely used and equally important when building any RAG based application. So I hope you now have a clear understanding of what RAG is, why it is needed, and what exactly happens behind the scenes when we work with retrieval augmented generation. So in the next chapter, we will move from theory to actual implementation, where we will build a real RAG application step by step and see how these concepts comes together in practical setup. So if you found this video very helpful, then don't forget to like, share and subscribe to support the channel. And if you have any questions, feel free to drop them in the comment section. I'll be happy to help you. And as I always say, keep learning, happy coding, and I'll see you in the next chapter, because the next chapter is going to be a very important. So stay tuned, and until then, have a great day.